Hello again, welcome back to the Strand tutorials. Today I'm going to show you a few final things that we've glossed over in the past, such as some properties and some attributes. And I'm also going to go through a list of common mistakes that people make when they're trying to use Strand. And so when you're having some of these issues, hopefully you'll be able to sort them out yourself. So I'm going to build the bridge again. I am going to make both sides of the bridge. I am going to put in these extra members like we spoke about trying to have a go at last week or last video. If you haven't tried to make this 3D bridge yet, I suggest you go and have a go. The only way that you will learn these tools is by trying them out for yourself. Watching somebody else do it doesn't teach you how to use them. Okay, so have a go at making this yourself, and then come back and watch this video. So I'm just looking at this in depth now, trying to think of the best one to make it. I know what I'm going to do. Alright, so let's make a node at 0, 0, 0, let's make one at 3, let's make one at 1.5 and 2.598. Yes, okay, let's make those elements. Let's grab all of that and go tools, copy by increment. 3 meters, let's do it twice. Apply, let's create that beam and that beam. Okay. Alright, I'm going to assume that this is 2 meters wide total. It looks like it's somewhere roughly around there. I'm going to show you the mirror tool. I didn't show you this last time. I didn't think you'd need it, but it's kind of cool, so I'll show it to you. I'm going to create a node at twice a mile. I'm going to create a node 1 meter away in the Z direction. So we've got that node there. I want to build the other side of the bridge. What I'm going to do is go Tools, Mirror. And what it allows me to do is select some geometry. So I want to select all of my beams. And I can actually mirror them about the YZ plane. YZ plane. Located at that point. That's definitely not what I wanted. YX plane. Sorry. XY plane. At that point. Cool. So basically what I've done is I've effectively made a mirror plane in here, and everything on this side of the mirror plane I'm going to put on that side. So I apply that, I get the other half of my bridge almost instantly. If you didn't want to use the mirror, I could have just gone Tools, Copy, by increment, in the Z direction, 2 meters, do it once, apply. That's actually the better way to do it. But I just wanted to show you the mirror plane because I didn't show it to you last time. I can get rid of that node. I don't need it anymore. I'm going to create some elements. So let's make some of them. I'm going to make my cross beams. They look thinner than everything else, so I'm going to make them a different property type. So I'm going to make them property type 2. Join everything up. Now it's entirely plausible that the ones on the bottom would actually be different to the ones on the top. In reality they probably are, but I've just joined them up as all the same elements at this stage. Cool, so I've got my box girder bridge now. Hopefully you got something similar when you were playing around at the end of last week. There is a whole bunch of different ways to have made this. Whatever way that you saw fit, it doesn't really matter. Okay, so we've got this. Few things that we might want to look at. We did mention very briefly in the first set of videos that if we wanted to put our forces on these nodes, we went node attributes. Attributes of a node is a force or a restraint, and that's all we talked about. There's a whole bunch of other options here, so anything that you could think about wanting to apply to a node is probably an attributes node. Alright, so if you want to apply something to your system, it's probably an attribute. Force and restraint are by far the two most common, but as you get to more complicated systems, you're going to want to start putting in temperatures and heat sources and things like that. Definitely not in this course, but in some of your other courses. Yes, you can do thermal expansion solves, or you can actually do thermal conductivity solves as well, which is cool. You can apply things to more than just nodes. You can apply properties to beams. So if you have a distributed load, which was mentioned in the notes on structures, so a force that goes across, uniformly distributed across a beam, you can come and apply that to a beam using either a force principle or a force global, and put those types of forces in here. You can give a taper to a beam. You probably don't need to use that, but if for some reason you do actually want to make your beams get thinner as they go to one end, yes, you can do that. So you have a whole bunch of properties in here. I'm going to create a plate as well. So this is the next level of complexity. When you go from nodes to beams, you can go also and make a plate. So whilst a beam is one-dimensional, so it's long, plates are two-dimensional. They're defined by an area. So if you want to make a plate, you can make triangular plates or square plates. A quad 4 is a square plate that I'm going to make here. We can put in a plate by joining up 4 nodes. Why is this relevant? Well, because considering this thing is a bridge, it probably doesn't just have a few beams across. It probably has plates in here. Yep, that's definitely connected to the wrong spot. Probably has plates in here to operate as the road. If you did have a road like this, you might not really think that point forces are the correct way to apply your loads. You might want to say that in reality what we have is something much more similar to a pressure on these plates. And you can do that. So that would simply become an attribute of a plate can be a face load. And you can put a pressure on that. And then you can just work out whatever pressure you would need to determine the loads, evenly distribute them across your plate. However, what's going to happen when you do that, you put a pressure on this plate. I'll do it on it as well. Let's put a face load, normal pressure on that plate of 1 Pascal, doesn't really matter. I've now got a pressure on that plate. All it will really do is distribute that pressure evenly amongst these 4 nodes and apply it as 4-point loads to the nodes. So there is actually in the simulation no real difference to applying a pressure versus applying distributed point loads. It's just whatever is easiest for you. Right, I'm going to get rid of the plates. Unless you absolutely have to, basically don't use them. They're just going to cause you far more harm than good. So I'm going to come to plate, select, I'm going to select all, and I'm going to do it. Right, our plates are gone. They are there, they do exist. You hopefully don't need them. If you do need them, be very, very careful that you're not doing anything incorrect when you're using them. Be very careful that you're not getting errors. Okay, so that's kind of the attributes tab covered. If you want to apply things to nodes, beams, or plates, whether they're forces or restraints or temperatures, you generally do that through attributes. The other thing we're going to talk about is properties. You have seen these before. I'm going to talk about them again though. Properties of a beam. You can come in here and give your beam type a set of properties. These are there is a library of predefined materials, which is steel, which you can assign, or you can simply come and type into here the properties that you have. So if you go out and you get some weird and wonderful copper alloy to put into your structure for some reason, and its material properties are not in here, you can just enter them in yourself. We also need to always give our system geometry. Come in and pick whatever cross section it is that you have. If you are buying common materials, they are almost certainly going to be solid bar, solid round bar, height, solid square bar, or RHS. They're by far the most common, but if you know a little bit more about how your loadings are going to work, you might be able to use things like I-beams and C-sections in order to make stronger, lighter structures. But make sure you pick some geometry, you give it some dimensions. Actually, I'm going to put these in meters. Remember how I said last week that this happens all the time? Because cross sections are done in millimeters, often you go, oh, I've got 25 by 25, I'll assign that. I'm just going to show you what it looks like. When you redraw, that's what it looks like. So if you ever get a model that looks like this is because I said that my cross sections were 25 meters by 25 meters and only 3 millimeters thick. 3 meters thick, sorry. This is probably what you got wrong. So it's a property, beam, geometry, at 0.025 and 0.025. So on that. Close, I'll just redraw. There we go, that's good. So that's property type 1 that I fixed there. I've got 2 different beam property types, so I need to come and edit property type 2 as well. Okay, tell it what material I want it to be. It can be glass. That's a terrible idea, but let's make it glass anyway. Glass I-beam. Go and put in whatever numbers you have. That's going to be easier. That not work. Okay. What? Yes, there we are. Just very quick. Awesome. Okay, so now I've come in and I've made my properties what I wanted them to be. I can put my forces on and my restraints on, and I can go and solve that. But I'm going to solve first without them, because I want to show you the error that you get. So you come in and you solve here. It'll think about it. It shouldn't think about it for that long. Okay. I don't know why that took 6 seconds, but anyway. That's why it did. Okay. We come up to our warning here. Global matrix contains large pivot ratios. This could indicate ill-constrained problem. Basically what it means is I didn't fix this thing to the world in any way, shape or form. So it basically just got a rounding error and just disappeared off into space. If this will happen to you if ever you don't fully restrain your model. It's called rigid body motion, where the whole thing doesn't bend or anything, it just shoots off into space because you've not actually tied it to the ground in any way. So that's because I haven't gone in and put in my restraints. So I want to fix these. Apply. I want some rollers on that end. Apply. I want to put some loads in. Force. And those. Cool. Solver, mini static. Solve, yes. That's better. 1 second. Completion time. Awesome. What you want to do is solve early. Generally, have a look. Make sure that everything is moving the way you expect it to. Yes, that all looks good. Wonderful. Okay. So I've done this. I've made a simple model. I've solved it, it all works, everything seems to be okay, I haven't made any mistakes yet, but I look back at this and I realized that, hey, I've forgotten to put in my cross braces and these ones going down, and I have a real good look and I go, those ones on the end are definitely bigger than these ones in the middle. Maybe I should change that. So putting in the cross braces is easy. All I have to do is create a new element with a new property type, because it's going to have different dimensions to the ones before. So property type 3 this time, and I have these cross braces in there. So that's quite simple. Great. If I want to do the ones that drop down, so I'm talking about these vertical hanging ones here, that's a little trickier. I don't have a node in here that I can join to. So I can drop, if I try to create an element now, being property type 4, I don't actually have anything down here to connect it to. Not the end of the world, this happens all the time. This is where we can use our subdivide tool. So I'm going to go Tools, Subdivide, and I'm going to split my beam into 2. Evenly in 2 because I want to split right in the middle. I'm going to grab all of these beams. I'm going to hit apply. I don't know if you can see, but I now have a node in the middle. I will make my nodes bigger. Sorry, I'm not sure how well these are going to be displaying on your monitors. So there we go, bigger nodes. We now have nodes in the middle. I can now come and create in property type 4, which joins that to that, that to that. Good enough, yes. And there we go. Cool. So that was being property type 4 is now in. The only thing that I wanted to do was come and grab these members here, that one, that one, that one, that one, and make them bigger. Because if I have a look at my image, they are much thicker, clearly, than the ones on the sides. So I want to make these thicker, but if I just come and I change the properties of beam type 1 so that they're bigger, which I could just come in here and change that, it would change the property of all of beam type 1. So it would change all of these ones to be thicker as well. Effectively, what I want is for these not to be beam property type 1. I want them to be a new property type. But it is an attribute of a beam is its property type. So it's currently 1, is 6, so it is 6. Apply that. And there we go, they're now being property type 6, they're different again. Alright, now I have a whole bunch of new properties in here. Property, beam, 1 we set, 2 we set, but 3, 4, 5 and 6, all it's doing is just reusing the properties for beam type 2, but often it'll just leave these blank. So you're going to have to come in for every one of these and say, no, you're not window glass. You're going to be an aluminium alloy. You're going to be flat bar, which is 20 by 3, for example. Sign. Come through, put all of your properties in for all of your different materials. You can obviously reuse the same ones over and over again if you want, but generally the reason you've got different property types is because you wanted to make them out of different types of members. I forgot to give it a thickness. Because I made it thicker than it was round. That doesn't work, do it? So, cool. Now we have all of our beams in there. Now we should be able to solve again. Yes, overwrite. No errors, no warnings, that's excellent. Check our results out. Oh look, everything is bending in quite a different way to the way that it did before. Just as a side note, I did actually make these thinner, which is probably not the smartest idea when it comes to building one of these structures. But you can see that we've clearly drastically changed the way that our structure is behaving as a result of adding these new elements. We can come and put some contours of stress, total fiber, always total fiber. And we can have a look and say, okay, there is an awful lot of stress in those members, which we expected. There is a little bit of stress in these ones, very little stress in, say, these end members. And that makes sense because there's nothing that's really trying to compress or tension the bridge in the Z direction. Nothing's trying to pull these two things apart. So you would expect these members not to be holding a lot of load. Okay, so basically that's properties. The reason that I talk about them so much is by far the most common error that you see in Strand is people not having a Young's modulus in for their property type when they try to solve. Okay, this is the one most commonly will come up, and that should have given me an error. Why did that not give me an error? You have no modulus. How did that work? There we go. So, when you have no modulus, you will get an error. Your error will be global stiffness matrix is similar. Alright, so if ever you're seeing that error, the first thing to check is always that every one of your members, whether they're beams or plates, you've got to check everything that you've used, make sure that it all has modulus and Poisson's ratio and all has geometry. Okay? That's what's going to get you most often. The next thing to check if you're still getting that error is that you have fully restrained your system, that you haven't accidentally missed a couple of nodes and that everything is just spinning around in space. The other thing that is really important when we talk about properties, if you remember back to the structures notes, I said there are two really important things, and they're Young's modulus and yield strength. So Young's modulus is what we put in here. Nowhere in Strand do we put in the yield strength. And that's because Strand doesn't deal with these sorts of things. Alright? It can't actually tell when something is going to break. It's a function of the solve that we're doing. So when we say we're doing a linear static solve, Strand assumes that everything is indefinitely strong. It all has a different stiffness, but nothing will ever break. So if you come in and you change these loads, so we go attributes of a node, force, we grab these and we put in a couple more zeros there, I apply that, I go solve a linear static, solve, yes. I didn't put my properties back in. As I said, this is the one that always gets you, it just got me. 6 as well, I think. There we go. Okay, if I look at how far my beam has, my bridge, has deflected, contours of displacement, y. We're talking over 100 mil here. We're talking almost 1 meter of deflection in something that's only 3 meters from there to there. That certainly will have broken under those sorts of loads. And if I go contours of stress, total fiber, apply. Stress is up here in the gigapascals, when we've got yield strength in the hundreds of megapascals. So 10 times the stress at which these things will have broken. Strand doesn't know and Strand doesn't care. You told it linear static, it doesn't care. This is where you need to activate your brain. Okay, this is where you need to look at your structure and say, this is not okay, I'm going to need to change something so that it works properly. There's only really one more thing that I want to talk about here, and it's summary model mass, volume, total length of things. These properties in here are very useful when you are trying to do things like strength to weight ratios, or trying to compare models for how much they might cost based on how much material they're using. You can come up and you can get your overall mass, meaning if you come in and you make some changes to this, you can see how it's affected your overall mass, and then maybe whether it's going to cost you more or less to build. So overall, that's Strand 7. It's probably not going to come super easy to you. Again, this is something that we teach third and fourth year students, so if you have to fiddle around with this for a little while before you're happy with it, that is to be expected. The only way that you learn these types of programs is by having a go. Okay, there is no, oh, this is 100% the right way to do it. Have a play, try to break it, have another go until you get comfortable playing around in this space. If you are having serious problems, by all means, contact me, talk to me, I will help work you through the process. But basically, good luck with your towers. Spend a bit of time, do a bit of research, and do some nice design work, and this should allow you to make really intelligent decisions about what you're doing. Enjoy it.